a mile underground in South Dakota, inside a cavern carved from a former gold mine. There is a titanium vessel the size of a school bus filled with 10 tons of liquid xenon, cooled to -148 degrees Fahrenheit. It is the most sensitive listening device humanity has ever constructed. 250 scientists and engineers from 37 institutions spent the better part of a decade building it. It cost $70 million. Its sole purpose is to detect dark matter, the invisible substance that makes up 85% of all matter in the universe. It has been listening for years now, and it has heard nothing. But that is not the part that should concern you. The part that should concern you is what it did hear. In December of 2005, the LZ experiment, short for Lux Zeppelin, announced the results from 417 live days of data collection, the largest dataset any dark matter detector has ever assembled. They found no dark matter. What they found instead were neutrinos from the Sun, particles that had traveled 93 million miles, passed through the entire Earth, and registered faintly in a detector buried a mile underground in an abandoned gold mine. The instrument works. It can detect particles arriving from the core of a star. It simply cannot find the one particle it was designed to find. And this was not the first time. LZ's predecessor, the LUX experiment, ran from 2013 to 2016 in the same cavern and found nothing. Before that, XEN-ON1T at Gran Sasso in Italy, 3.2 tons of liquid xenon under a mountain in the Apennines, came up empty. Its upgrade, XEN-ONTT, 8.6 tons, produced the same result. PandaX in China, operating in the deepest underground laboratory on the planet, 2.5 kilometers below a mountain in Sichuan province, saw no signal. The CDMS experiments using germanium crystals cooled to 15 thousandths of a degree above absolute zero found nothing either. Every experiment, every detector, every approach, the same answer. Over the past 35 years, the sensitivity of these detectors has improved by a factor of 100 million. That is 8 orders of magnitude. In 1988, the best experiments could rule out dark matter interactions above roughly 10 to the -40 square centimeters. By 2024, LZ had pushed that limit down to 2.2 times 10 to the -48 square centimeters. If you had told a physicist in 1990 that detectors would reach this level of sensitivity without finding anything, they would have told you that was impossible. The theoretically predicted cross-sections, the so-called WIMP miracle range, sits between 10 to the -44 and 10 to the -48. LZ has reached the bottom of that range. The parameter space that was supposed to contain dark matter has been almost entirely emptied out. And now there is a wall approaching. They call it the neutrino fog. Below a certain sensitivity threshold, detectors become so exquisitely tuned that they cannot distinguish a dark matter signal from the background noise of neutrinos produced by the sun, the atmosphere, and cosmic rays. LZ has already entered this fog at low masses. The December 2025 results detected solar boron 8 neutrinos at 4.5 sigma significance, confirming the detector is now sensitive enough that neutrinos are an irreducible background. Building bigger detectors will not solve this. You do not see through fog by opening your eyes wider. And there is one experiment that makes the situation even stranger. In a different laboratory, under Gran Sasso, The Dama/Libra experiment has been claiming to detect dark matter for over 20 years. Their method is different from the others. They look for an annual modulation, a seasonal variation in the detection rate that should occur because the Earth's orbital velocity alternates between adding to and subtracting from the Sun's velocity through the Milky Way's dark matter halo. In summer, we move faster through the halo. In winter, slower. More collisions in June, fewer in December. Dama/Libra claims to have detected this modulation at a cumulative significance of 13.7 sigma. That is an extraordinarily strong signal. If it were real, it would be one of the greatest discoveries in physics, but nobody else can reproduce it. The COSINE 100 experiment in South Korea, using the same sodium iodide crystal technology, ran for 6.4 years and found no annual modulation, challenging the Dharma claim at over 3 sigma. The ANAIS 112 experiment in Spain found results consistent with no modulation and inconsistent with Dharma's observation at nearly 3 sigma. In 2000, a combined analysis from both experiments, published in Physical Review Letters, effectively ruled out a dark matter origin for the Dharma/Libra signal. The Dharma team continues to maintain their claim. Nobody outside their collaboration believes them. This is the state of the field. One experiment says it found dark matter, and nobody can replicate the result. Every other experiment says there is nothing there, and the sensitivity threshold has improved by a factor of 100 million without a single confirmed detection. To put the scale of this enterprise in perspective, the xenon alone in the LZ detector cost roughly $14 million, 200 bottles at approximately $100,000 each, purchased from industrial gas suppliers who normally sell it for semiconductor manufacturing and medical imaging. 20% of LZ's budget went to buying a noble gas. The next generation experiment, which would use 40 to 50 tons of xenon, will cost even more, and the global supply of xenon is limited. Dark matter physicists have become some of the world's most improbable commodity traders, negotiating bulk purchases of one of the rarest naturally occurring elements on Earth to fill underground tanks that detect nothing. Think about what this means. Humanity spent decades and billions of dollars constructing instruments of staggering precision, buried them under mountains and inside abandoned mines to shield them from cosmic interference, cooled them to temperatures colder than deep space, and achieved 100 million-fold improvement in sensitivity. The result is not a discovery. The result is a war. The question nobody in the field wants to answer publicly is not, when will we find dark matter? The question is whether there is anything there to find. This is not speculation from the fringe. Joseph Howlett, a physicist working on the Xenon program, wrote in Scientific American in 2023 that the hunt for dark matter is in crisis, and that underground traps set on Earth to capture supposed dark particles have now spent years measuring nothing but subterranean silence. That phrase, subterranean silence, is worth sitting with for a moment, because the silence is not the absence of information. The silence is the information. To understand why that silence is so disturbing, you need to understand what dark matter actually is and how we know it exists. And that means going back to a man who saw the problem 90 years ago, was ignored for decades, and died before anyone admitted he was right. In 1933, a Swiss-Bulgarian astronomer named Fritz Zwicky was studying the Coma cluster at the California Institute of Technology. Zwicky was, by all accounts, a deeply unpleasant colleague. He called the other astronomers at Caltech spherical bastards because, as he explained with evident satisfaction, they were bastards every way you looked at them. When he was 32, he reportedly told his supervisor, the Nobel laureate Robert Millikan, that he had read every paper Millikan had ever written and could tell him quite categorically that he had never found a single original idea he could honestly call his own. Millikan challenged him to name one field where Zwicky could do better. Zwicky said, astrophysics. 3 years later, he and Walter Baade predicted the existence of supernovae, neutron stars, and cosmic rays from stellar collapse in a single paper. Kip Thorne later called it one of the most prescient documents in the history of physics and astronomy. But the prediction that mattered most was the one nobody listened to. Zwicky used the virial theorem to calculate the total mass of the Coma cluster based on the velocities of its member galaxies. The number he got was 400 times greater than what the visible stars could account for. Something massive was there, holding the cluster together, but it was invisible. He called it Dunkel Materia, dark matter. His estimate was off by roughly an order of magnitude because he was using an outdated value for the Hubble constant. But his core conclusion has been validated by every subsequent measurement for 9 decades. Zwicky also predicted gravitational lensing in 1937, the bending of light by massive objects acting as cosmic magnifying glasses. That prediction was not confirmed until 1979, with the discovery of the twin quasar QSO 957 plus 561. By then, Zwicky had been dead for 5 years. He passed away on February 8, 1974, at the age of 76. He had discovered 120 supernovae over 52 years of observing. He had earned the Presidential Medal of Freedom and the Royal Astronomical Society's Gold Medal. But the prediction that defined the next century of physics, the existence of dark matter, went largely unacknowledged during his lifetime. His daughter Barbarina remembers that everyone at Caltech would scatter when her father walked down the hallway. When Robert Oppenheimer published his neutron star physics in 1939, he did not cite Zwicky's earlier prediction. The offices were down the hall from each other. When researchers today talk about dark matter, they almost always start the same way. Zwicky noticed this in the 1930s. Nobody listened. He was not the only one. Jan Einasto, an Estonian astronomer, born in 1929 in Tartu, spent his career behind the Iron Curtain at the Tartu Observatory. His family name is an anagram of Estonia, chosen by his father to replace their German surname in a gesture of national pride. In 1974, Einasto and colleagues published a paper in Nature arguing that galaxy clusters must be stabilized by hidden matter. In 1977, he presented evidence that the universe has a cell-like structure with vast voids, an early detection of the cosmic web. He organized the first dark matter conference in Tallinn in 1975, a full decade before the first official International Astronomical Union conference on the topic. He did this partly to attract Western astronomers to Soviet Estonia, using dark matter as a bridge across the Cold War divide. The fundamental mystery of the universe doubled as a diplomatic tool. 4 decades later, a woman proved Zwicky right, and the world treated her almost as badly as it had treated him. Vera Rubin was born in 1928 in Philadelphia. As a girl, she built her first telescope from cardboard and a lens with her father's help and watched stars from her bedroom window. She graduated Phi Beta Kappa from Vassar as the only astronomy major in her class. When she applied to Princeton's graduate astronomy program, she was denied because of her gender. Princeton did not admit women to astronomy until 1975. At her first American Astronomical Society meeting, she presented her master's thesis while 22 years old and pregnant, and was met with harsh criticism. In 1965, Rubin became the first woman officially invited to observe at the Palomar Observatory. The application form read, "Due to limited facilities, we do not accept applications from women." Someone had handwritten "usually" above the printed text. When she arrived, the bathroom door said "men." She cut out a paper figure of a woman in a skirt, taped it to the door, and declared that the facilities problem was now solved. Working with Kent Ford at the Carnegie Institution, she measured the rotation curves of spiral galaxies. Ford had built an image tube spectrograph of unprecedented sensitivity, and Rubin chose to use it on a problem most astronomers considered boring: rotation curves. How far stars orbit the centers of galaxies. She chose it precisely because nobody else was looking, which meant she would not have to compete for telescope time. The work was painstaking. Each galaxy required long exposures, sometimes hours, while the telescope tracked the target across the sky. While waiting for photographic plates to develop, she ate ice cream cones. She once said that by the time she had eaten 4 cones, she could draw the rotation curve of Andromeda from memory. The curves were flat, star after star, galaxy after galaxy. The orbital velocities at the outer edges were the same as the velocities closer to the center. This should not happen. In a system where most of the mass is concentrated in the center, like the solar system, outer objects orbit more slowly. Mercury orbits the Sun at 47 kilometers per second. Neptune orbits at 5. If the Milky Way's mass were concentrated in its visible stars and gas, stars at the edges should orbit more slowly than stars near the bulge. They do not. They orbit at the same speed, or even slightly faster. This implies that the galaxies are embedded in enormous halos of invisible mass that outweighs the visible stars by a factor of roughly 5 to 1. By 1980, Rubin and her collaborators, including Norbert Fonnard, had documented flat rotation curves across more than 60 spiral galaxies. The evidence was overwhelming and reproducible across every galaxy type they measured. She received the National Medal of Science and the Royal Astronomical Society's Gold Medal, the first woman to receive it since Caroline Herschel in 1828, a gap of 168 years. She was mentioned repeatedly as a Nobel candidate. She never received the prize. She died on Christmas night, 2016, at the age of 88. The Nobel cannot be awarded posthumously. All 4 of her children earned doctorates in science. The Vera C. Rubin Observatory in Chile was renamed in her honor in 2019, and in June of 2025, her face appeared on a United States quarter. So the evidence that something out there is exerting gravitational force is beyond dispute. Galaxy rotation curves, gravitational lensing, the cosmic microwave background, the large-scale structure of the universe, the bullet cluster. Every major observation in astrophysics for the past 50 years confirms that roughly 27% of the universe's mass energy content is made of something invisible that interacts through gravity. But the evidence that this something is a particle, a thing you could catch in a detector, a thing made of stuff in the way that protons and electrons are made of stuff, that evidence does not exist. 40 years of searching, at 100 million times the original sensitivity, has produced nothing but increasingly precise silence. And in 1995, while the detection experiments were ramping up, while the physics community was pouring resources into building ever larger tanks of liquid xenon, a physicist at the University of Maryland named Ted Jacobson published a short paper in Physical Review Letters that almost nobody outside theoretical physics paid attention to. He derived Einstein's field equations, the foundation of general relativity, the equations that describe how matter curves space-time, not from geometry, from thermodynamics, as if gravity were not a fundamental force at all, but a macroscopic consequence of something deeper, as if space-time itself were not the stage on which physics plays out, but something that emerges, like temperature emerges from the motion of molecules you cannot see. That paper will matter later. Remember it. For now, what matters is this. Dark matter is real. The gravitational evidence is ironclad, but the particle is missing. And instead of confronting what that absence might mean, the physics community has spent 4 decades building more sensitive versions of the same experiment, expecting a different result. But the failure to detect dark matter particles is not the disturbing part. The disturbing part is what happened when a physicist in Israel decided to stop looking for the particle and start questioning gravity itself. In 1981, a physicist named Mordechai Milgram was sitting in his office at the Weizmann Institute of Science in Rehovot, Israel, and he was staring at galaxy rotation curves, the same flat curves Vera Rubin had documented, the same data that everyone else interpreted as proof of invisible mass. But Milgram was not thinking about invisible mass. He was thinking about the acceleration. He noticed something nobody else had noticed, or at least nobody else had taken seriously. The discrepancy between Newtonian predictions and observed rotation curves did not appear at a specific distance from the galactic center. It did not appear at a specific velocity. It appeared at a specific acceleration, roughly 1.2 times 10 to the negative 10 meters per second squared. Below that threshold, galaxies behaved as if gravity were stronger than Newton said it should be. Above it, everything looked normal. One number. That is all it took. Milgram spent the next 2 years writing 3 papers, proposing that below this critical acceleration, the law of gravity itself changes. He called it modified Newtonian dynamics, or MOND. He submitted the first paper to Nature. They rejected it. He submitted to Astronomy and Astrophysics letters. Rejected again. He eventually published all 3 papers in the Astrophysical Journal in July of 1983. Robert Sanders, who later wrote a historical review of the theory for the Canadian Journal of Physics, described it plainly. MOND is solely the invention of Mordechai Milgram. In the early 1980s, no one but Milgram had considered such a modification. It was a brilliant stroke of insight. The physics community responded by ignoring it. Not because it was wrong. The predictions were disturbingly accurate. With that single parameter, Milgram's formula fit galaxy rotation curves across an enormous range of galaxy types, masses, and luminosities. Standard dark matter models require multiple adjustable parameters to fit each galaxy individually. You need to specify the density profile of the dark matter halo, the concentration parameter, the scale radius, and you have to tune them separately for every galaxy. Milgram needed one number, the same number, every time. And it got worse. MOND made predictions that were later confirmed. Low surface brightness galaxies, which are diffuse and have very low internal accelerations, should be entirely in the deep MOND regime, according to the theory. Milgrom predicted they would show large mass discrepancies at all radii and slowly rising rotation curves. This was before low surface brightness galaxies had been well observed. When the observations came in, they matched, not roughly, precisely. Dark matter models had to be retroactively adjusted to accommodate what MOND had predicted in advance. MOND also predicted a specific relationship between the total baryonic mass of a galaxy and the flat rotation velocity of its outer stars. This is called the baryonic Tully-Fisher relation. The prediction is that mass is proportional to the fourth power of velocity, with a proportionality constant determined entirely by Milgrom's acceleration and Newton's gravitational constant. Zero free parameters, no fitting, and across hundreds of galaxies spanning several orders of magnitude in mass, from tiny dwarfs to massive spirals. The relationship holds with a tightness that dark matter models can accommodate, but cannot naturally explain. And then there is the external field effect. This is a prediction unique to MOND that has no analog in standard dark matter theory. In Newtonian physics and in general relativity, the internal dynamics of a system are not affected by a uniform external gravitational field. This is called the strong equivalence principle. If you are in a box falling freely in a gravitational field, you cannot tell you are falling. The internal physics of the box is the same regardless of the external field. MOND violates this principle. In MOND, the internal dynamics of a galaxy or a star cluster depend on the external gravitational field from surrounding structures. A dwarf galaxy orbiting a massive host galaxy should have different internal dynamics than the same dwarf galaxy in isolation, even if the tidal forces are negligible. Milgrom predicted this in the 1980s. 30 years later, in 2000 to 2000, Che, Lely, Desmond Magar, Lee and Schombert published a detection of this effect in the Astrophysical Journal, using rotation curve data from galaxies in different external field environments. The data matched MOND's prediction, an effect that no dark matter model predicts, an effect that violates a principle Einstein considered fundamental, had been predicted 3 decades before it was observed, and confirmed by a dataset the theory was not designed to fit. Think about what that means. A formula written in 1983 by a single physicist, rejected by the leading journals, ignored by the mainstream, predicts the behavior of galaxies that have not yet been observed with zero adjustable parameters. And the mainstream response was not to investigate. It was to treat the man who wrote it as professionally radioactive. Milgrom spent the next 4 decades at the Weizmann Institute, holding the Isidore Rabi Chair of Physics, publishing steadily, refining his theory, and being largely excluded from the conversation. He was not fired, he was not formally censured, he was simply not invited. When the dark matter community held conferences, MOND was not on the agenda. When grants were distributed, MOND research was not funded. The silence was institutional and thorough, but the data did not cooperate with the silence. In 2016, 3 physicists, Stacy McGaw, Federico Lely, and James Schombert, published a paper in Physical Review Letters that should have detonated the dark matter consensus. It did not. But what it showed was extraordinary. They had assembled the SPARC database, a collection of rotation curves for 153 galaxies with high-quality photometric and kinematic data. For each galaxy, they calculated two things at every measured radius. First, the observed total radial acceleration, which you get from the rotation curve. Second, the acceleration you would expect from the visible baryonic matter alone, calculated from the distribution of stars and gas, using standard mass-to-light ratios. Then they plotted one against the other. 2,693 data points. 153 galaxies of wildly different masses, sizes, morphologies, and surface brightnesses. The result was a single, tight curve, a universal relation between observed gravitational acceleration and baryonic gravitational acceleration that held across every galaxy in the sample, with an observed scatter of just 0.13 dex, most of which could be attributed to measurement uncertainty rather than physical variation. More recent analyses by Desmond in 2023 found the intrinsic scatter may be less than 0.034 dex. That is astonishingly tight for an astrophysical relation. This is called the radial acceleration relation, or RAR, and it is one of the most uncomfortable results in modern astrophysics. Here is why. In the standard dark matter picture, dark matter halos form from gravitational collapse during the early universe. Their structure is determined by the initial conditions of the density field, the merger history of the halo, and the dynamics of structure formation. This process is largely independent of what the baryons, the ordinary matter, the stars and gas, are doing. The baryons fall into the dark matter potential wells, but they do not determine the structure of those wells. The dark matter distribution should have its own independent character. If that is true, there is no fundamental reason why the dark matter distribution at every radius in every galaxy should be perfectly predictable from the baryonic distribution alone. And yet it is. If you tell me the distribution of visible matter in a galaxy, I can tell you the total gravitational field. I do not need to know anything about the dark matter halo. The dark matter, if it exists as a separate substance, somehow knows exactly where the baryons are and arranges itself in a precisely correlated way in every galaxy, regardless of mass, size, or history. This is not a rough trend. It is a law. Milgram's MOND predicted this from the beginning. In MOND, there is no separate dark matter substance. The gravitational acceleration is determined entirely by the baryonic mass distribution, modified by the transition function at low accelerations. The RAR is not a coincidence in MOND. It is the theory. Now, let me tell you about the man who discovered this relation and what it cost him. Stacy McGaw was born in 1964. He earned his bachelor's degree from MIT in 1985 and his doctorate from the University of Michigan in 1992. He is currently a professor of astronomy at Case Western Reserve University and director of the Warner and Swasey Observatory. He has accumulated over 24,600 citations on Google Scholar. He is, by any measure, a successful and accomplished astrophysicist. He was also, for most of his career, a true believer in dark matter. In the late 1980s and early 90s, McGaw specialized in low surface brightness galaxies. He built a model within the dark matter framework that made two predictions. First, that low surface brightness galaxies should be less clustered than bright galaxies. That prediction was confirmed. Second, that they should deviate from the Tully-Fisher relation. That prediction failed. Spectacularly. He tried, by his own account, what seemed like 1,000 ways to reconcile the data with dark matter. Nothing worked. And then someone pointed him towards MOND. Milgram's theory predicted exactly what McGaw was seeing. His reaction, he later wrote, was great. Now I have the data to disprove this stupid theory. He compared Milgram's predictions against his own observational data. And, in his words, darned if they did not all come true. McGaw has described what happened next as the most difficult struggle he ever faced in his career. He barely slept for nearly a week. Admitting that MOND fit his data better than dark matter models was, professionally, an act somewhere between courage and self-destruction. A grant proposal suggesting that MOND's predictions should be investigated was rejected. Harshly, he started a blog called Triton Station in 2016, partly as a way to discuss the evidence publicly when the journals and conferences would not give it adequate attention. In a December 2020 post titled 25 Years a Heretic, he chronicled the professional cost of following the data where it led. The pattern is hard to ignore. Zwicky saw the missing mass and was treated as a crank. Rubin measured it and was denied the Nobel. Milgram proposed an explanation that fit the data and was rejected by nature. McGaw tested it and found it worked and had his funding cut. At a certain point, the question stops being whether the theory is correct and becomes why the institutions tasked with evaluating evidence are so resistant to evaluating this particular evidence. You have probably been told that MOND was killed by the bullet cluster. This is one of the most repeated claims in popular science, and it is wrong. The bullet cluster, formerly designated 1E0657-56, is a pair of galaxy clusters that collided roughly 150 million years ago. The collision was observed using the Chandra X-ray Observatory and gravitational lensing data. What makes it famous is the spatial separation. The hot gas from the two clusters, which represents the bulk of the baryonic mass, slammed together and slowed down. But the gravitational potential, traced by lensing, kept moving with the galaxies. The mass and the gravity separated. In 2006, Douglas Clow and collaborators published a paper calling this a direct empirical proof of dark matter, because the gravity was centered on regions where the visible mass was not concentrated. The claim became the standard response to anyone who mentioned modified gravity. The bullet cluster proves dark matter. End of discussion. But Clow's paper made no attempt to analyze the bullet cluster using MOND or any relativistic extension of it. Within the same year, Angus, Famay, and Zhao published an analysis in the monthly notices of the Royal Astronomical Society showing that TeVeS, the relativistic version of MOND, developed by Jacob Bekenstein, does reproduce the gravitational lensing offset in the bullet cluster. MOND has always acknowledged that it needs some form of unseen mass in galaxy clusters, most likely ordinary neutrinos with a small mass. The bullet cluster does not contradict this. It contradicts a version of MOND that nobody was actually proposing. And there is something else. The collision velocity of the bullet cluster subcluster, roughly 4,700 kilometers per second, is extremely difficult to produce in standard cold dark matter simulations. Multiple studies have found that velocities this high have a probability of less than 1 in 10,000 in the LCDM framework. In MOND, the deeper gravitational potential wells naturally produce higher infall velocities, making the bullet cluster less surprising, not more. And then there is the train wreck cluster, Abel 520, which shows the opposite pattern from the bullet cluster. The dark matter peak coincides with the gas, not the galaxies. If the bullet cluster proves dark matter, then Abel 520 unproves it by the same logic. The community's response was to treat the bullet cluster as a smoking gun and Abel 520 as an anomaly. That is not how evidence works. The bullet cluster did not kill MOND. It was used to excuse the physics community from having to think about MOND. Those are different things, but here is where it gets worse, because the number at the center of MOND, Milgram's acceleration constant, is not just a number. It is suspiciously close to something else entirely, something cosmic. And that coincidence is either the most extraordinary accident in the history of physics, or it is a clue that the problem is far larger than galaxy rotation curves. Milgram's acceleration constant, A0, is approximately 1.2 times 10 to the negative 10 meters per second squared. If you take the speed of light, 3 times 10 to the 8 meters per second, and multiply it by the Hubble constant, the rate at which the universe is expanding, you get a number that is within a factor of roughly 5 or 6 of a zero. If you use the precise formulation that Erik Verlinde derived in 2016, C times H0 divided by 6, you get approximately 1.1 times 10 to the negative 10 meters per second squared. That is within 30% of the value that fits galaxy rotation curves. This should not mean anything. The Hubble constant describes the expansion of the entire observable universe, a phenomenon operating on scales of billions of light years. Milgram's constant governs the dynamics of individual galaxies, objects tens of thousands of light years across. In the standard picture of physics, there is absolutely no reason for a galactic scale acceleration threshold to be connected to the expansion rate of the cosmos. They are different phenomena operating at different scales, governed by different aspects of physics, and yet the numbers match. If this were a one-time coincidence, you could dismiss it. Numbers in physics sometimes happen to be close to each other, but this is not a one-time coincidence. MOND's acceleration scale appears everywhere you look once you know what to look for. It shows up in the dynamics of galaxy clusters. It shows up in the external field effect, a prediction unique to MOND, where the internal dynamics of a system are affected by the gravitational field of its environment, violating the strong equivalence principle. That effect was predicted by Milgram in the 1980s and detected by Che, Lely, Desmond, McGaw, Lee, and Schombert in 2020 using galaxy rotation curve data from the Astrophysical Journal. It shows up in the tightness of the radial acceleration relation. It shows up in the baryonic Tully-Fisher relation. Every time a new dataset probes the low acceleration regime, the same number appears. Either this is the greatest numerical accident in the history of science, repeated across thousands of independent observations, or it is telling you something fundamental about the universe that the standard model of cosmology is not equipped to explain. There is a physicist who believes it is the latter, and his proposal is among the most radical ideas in modern theoretical physics. Erik Verlinde was born on January 21st, 1962, in Woudenberg, in the Netherlands. He has an identical twin brother, Herman, who is also a string theorist and now holds a professorship at Princeton. Erik studied physics at Utrecht University under Gerard 't Hooft, who later won the Nobel Prize. His career trajectory was conventional and extraordinarily successful. the Institute for Advanced Study in Princeton, the Theory Division at CERN, a full professorship at Utrecht by the age of 34, then a move to the University of Amsterdam, where he remains. In 2011, he received the Spinoza Prize, the highest scientific award in the Netherlands, which carries a grant of €2.5 million. He was one of the most respected string theorists in Europe. He had tenure, prestige, funding, and the intellectual pedigree that comes from being trained by a Nobel laureate. He had every incentive to keep doing what he was doing, and no professional reason to risk his reputation on a radical proposal about the nature of gravity. None of this sounds like the biography of a heretic, but in 2010, Verlinde published a paper that put him on a collision course with the entire edifice of modern physics. And what made the backlash particularly telling was that Verlinde was not some outsider making claims from the margins. He was an insider, a string theorist with impeccable credentials, proposing that the field he had spent his career in might be approaching gravity from the wrong direction entirely. The resistance he faced came not from people who could find errors in his mathematics. It came from people who found the conclusion uncomfortable. The paper was titled On the Origin of Gravity and the Laws of Newton. In it, Verlinde argued that gravity is not a fundamental force. It is an entropic force, a macroscopic consequence of the tendency of microscopic degrees of freedom to maximize entropy. The way that temperature is not a fundamental thing, but an emergent description of molecular motion. The way that pressure is not a property of individual air molecules, but a statistical effect of their collective behavior, using the holographic principle, which says that the information content of a region of space is encoded on its boundary, and the unruh temperature, which describes the thermal radiation seen by an accelerating observer. Verlinde derived Newton's law of gravitation from first principles, not from geometry, not from curvature, from information and entropy. His own reaction to the derivation was revealing. He wrote that these equations do not just come out by accident. He was not claiming to have found a small correction. He was claiming that gravity itself, the force you feel holding you to your chair, the force that bends light around galaxies and holds the solar system together, is not fundamental. It is a thermodynamic consequence of something deeper. The physics community responded with a mixture of fascination, skepticism, and in some corners, hostility. Nobel laureate Gerard Hooft, Verlinde's own former advisor, expressed reservations. Others called the idea not even wrong, the most dismissive epithet in theoretical physics, meaning it is not clear enough to be tested. But Verlinde did not stop there. In 2016, he published a second paper, Emergent Gravity and the Dark Universe, in SciPost Physics. This paper extended his framework to de Sitter space, which is the kind of spacetime that describes a universe with a positive cosmological constant, which is to say, our universe. In de Sitter space, there is a cosmological horizon. That horizon has entropy proportional to its area, just like a black hole horizon. Verlinde argued that this entropy is not merely a formal analogy. It is physically real, and it contributes a volume law entropy term in addition to the area law term. When matter is placed in this space-time, it displaces some of this entropy. The space-time responds. It exerts what Verlinde called an elastic response, a force that acts on the matter as if there were additional gravitational mass present. What we have been calling dark matter in this framework has nothing to do with particles or substances, It is the reaction of space-time itself to the presence of ordinary matter. And the characteristic scale of this reaction, the acceleration below which it becomes significant, is naturally of order c times h0. The Hubble constant is not accidentally connected to Milgrom's acceleration. In Verlinde's framework, it is the reason for it. This is the point where the coincidence stops being a coincidence and starts being a prediction. In 2017, a team led by Margot Brouwer tested Verlinde's predictions against weak gravitational lensing data from 33,613 galaxies in the Kea survey. Verlinde's formula, with 0 free parameters, no fitting, no adjustment, matched the observed lensing signal. The paper was published in monthly notices of the Royal Astronomical Society. It was not definitive. The uncertainties were large enough that both Verlinde's prediction and standard dark matter models could fit the data. But the fact that a 0-parameter prediction from a theory that says dark matter does not exist matched the lensing data as well as dark matter models with adjustable parameters should have been front-page news. It was not. And then in 2021, something happened that changed the theoretical landscape permanently. Konstantinos Skordis and Tom Zlosnik, working in Prague, published a paper in Physical Review Letters titled New Relativistic Theory for Modified Newtonian Dynamics. For decades, the single strongest argument against MOND had been that it was an empirical formula, not a complete theory. It could fit galaxy rotation curves, but it could not reproduce the cosmic microwave background, the relic radiation from the early universe, whose detailed pattern of fluctuations is the crown jewel of modern cosmology. The CMB power spectrum is exquisitely well fit by the standard LCDM model, with 6 parameters. If MOND could not match it, MOND was dead as a fundamental theory regardless of how well it worked for galaxies. Skordis and Zlosnik showed that it could. Their theory, which involves a vector field and a scalar field in addition to the metric tensor of general relativity, reproduces both the CMB power spectrum and the matter power spectrum, while recovering MOND phenomenology in galaxies. Magor, who had spent 25 years watching MOND's empirical predictions come true, while being told the theory was fundamentally incomplete, called it a huge breakthrough. For years, stretching into decades, he said, people have largely ignored MOND because it seemed impossible to do what Skordis and Zlosnik have now done. David Spergel of the Flatiron Institute, one of the principal investigators of the WMAP satellite that mapped the CMB, dismissed the theory as baroque. He argued it effectively posits a complex form of dark matter. This is a revealing criticism. The argument is no longer that MOND cannot work. The argument is that it works, but the mechanism it requires is complicated. Coming from a community that has spent 40 years searching for an invisible particle that interacts only through gravity and has never been detected, the objection that an alternative is too complicated carries a certain irony. But here is what sits underneath all of this, the thing I mentioned at the start that you should remember. Verlinde's entire framework rests on a specific idea about the nature of gravity and space-time. That idea did not originate with Verlinde. It originated with Ted Jacobson. In 1995, Jacobson published a paper in Physical Review Letters with the title Thermodynamics of Spacetime, the Einstein Equation of State. It is 4 pages long. It has accumulated over 1,200 citations, and its central result is one of the most unsettling conclusions in the history of theoretical physics. Jacobson started with 3 ingredients: the proportionality between entropy and horizon area, which comes from black hole thermodynamics, and the work of Bekenstein and Hawking; the Clausius relation from thermodynamics, which connects heat flow, temperature, and entropy change; and the Unruh temperature, which gives the temperature experienced by an accelerating observer. From these 3 ingredients, Jacobson derived Einstein's field equations, the equations that describe how matter tells space-time how to curve, and space-time tells matter how to move. The foundation of general relativity, the bedrock of our understanding of the cosmos. His conclusion was stated with a clarity that makes it hard to misunderstand. He wrote that viewed in this way, the Einstein equation is an equation of state. He then added that this perspective suggests it may be no more appropriate to canonically quantize the Einstein equation than it would be to quantize the wave equation for sound in air. Think about what that means. The wave equation for sound in air describes how pressure waves propagate. But sound is not fundamental. Sound is an emergent property of air molecules moving around. The wave equation is a macroscopic description. You would not try to quantize it because it is not describing anything fundamental. Jacobson is saying that Einstein's equations, the equations governing gravity, the equations that describe the curvature of space-time, might be in the same category. They may not be fundamental, may not describe the deep structure of reality at all, but instead offer a macroscopic approximation of something we have not yet identified. If gravity is emergent, like temperature, then space-time is emergent too. It is not the fabric of the universe. It is a statistical description of something deeper. And dark matter, the thing we have been trying to catch in tanks of liquid xenon for 40 years, might not be a thing at all. It might be a feature of the emergence, a property of the approximation, a shadow cast by the real structure onto the surface of the description we are capable of perceiving. Verlinde's 2016 paper makes this explicit. In his framework, dark matter effects arise because we are using general relativity, an emergent, approximate description of gravity, and applying it in a regime where the approximation breaks down. The low acceleration regime, below milligrams of zero, is precisely where the emergent description starts showing its seams. The dark matter we are looking for is not there. The equations are breaking. And if the equations are breaking at the level of individual galaxies, then you would expect them to be breaking at the level of the universe too. You would expect the standard model of cosmology, built entirely on general relativity, to show cracks. You would expect measurements to stop agreeing with each other. You would expect the model to start failing. In March of 2025, a telescope in Arizona delivered evidence that this is exactly what is happening. At the summit of Kitt Peak in Arizona, on a 4-meter telescope built in 1973, there is an instrument that contains 5,000 robotic fiber optic positioners, each one thinner than a human hair, each one capable of independently targeting a different galaxy or quasar in the night sky. Every 2 minutes, the 5,000 fibers reconfigure, swinging to a new set of targets. On a good night, this instrument observes more than 100,000 galaxies. It is called the Dark Energy Spectroscopic Instrument, or DESI. The collaboration involves more than 900 researchers from over 70 institutions across the world, managed by Lawrence Berkeley National Laboratory. It began surveying in May of 2021, and the data it has produced is, depending on who you ask, either the most exciting or the most alarming result in cosmology in 25 years. In March of 2025, DESI released its data release 1, containing 18.7 million objects, approximately 13 million galaxies, 1.6 million quasars, 4 million stars, 270 terabytes of data, more than twice as many extragalactic objects as all previous three-dimensional spectroscopic surveys in history combined. To call it a dataset undersells what it represents. It is the most detailed, three-dimensional map of the observable universe that has ever existed. The purpose of this map is to measure baryon acoustic oscillations, or BAO. These are relic sound waves from the early universe, frozen into the distribution of galaxies like ripples in a cosmic pond. They serve as a standard ruler, a known physical size imprinted at a known time. That allows you to measure distances and expansion rates across billions of years of cosmic history. By measuring BAO at different redshifts, you can reconstruct how the expansion of the universe has changed over time. And that tells you about dark energy, the mysterious force driving the accelerating expansion. The Standard Model of Cosmology, LCDM, says dark energy is the cosmological constant, Einstein's lambda. It has a fixed value. It does not change. Its equation of state, the ratio of pressure to energy density, is exactly -1. Always has been, always will be. This is the simplest possible form of dark energy, and for 25 years, it has fit every major dataset within uncertainties. DESI's first results were presented on April 4th, 2024, at the American Physical Society meeting. They analyzed over 6 million extragalactic objects in 7 redshift bins spanning from roughly 1 billion years ago to 11 billion years ago. And the data preferred something other than a cosmological constant. Physicists parameterize possible variations in dark energy using 2 numbers, W0 and WA. W0 is the equation of state today. WA measures how it changes over time. For a cosmological constant, W0 equals -1 exactly, and WA equals 0. DESI's data preferred W0 of approximately -0.7, which is greater than -1, and WA of approximately -1, which is less than 0. What this means, translated from the formalism, is that dark energy appears to have been stronger in the past than it is today. It is weakening. The year 1 significance was modest, 2.6 sigma, with DESI and CMB data alone. That is suggestive but not conclusive. But when combined with supernova datasets, the significance climbed, 3.5 sigma with the Union 3 supernovae, 3.9 sigma with the Dark Energy Survey 5-year supernovae. The hint was consistent, persistent, and it pointed in the same direction regardless of which supernova catalogue you used. Nathalie Palanque-Delabrouille, co-spokesperson for DESI at Berkeley Lab, described the private, unblinding moment in December of 2023. The blinded data had shown a huge divergence from LCDM. When the real data were unveiled, the team initially felt relief that the points came close to the standard model. Then they noticed a small, persistent deviation. It was not noise. It did not go away when they changed their analysis methods. It sat there, stubbornly, at the 2 to 3 sigma level. Then came March of 2025. DESI released its Year 3 results, drawn from a data set that had roughly doubled in size, over 14 million galaxies and quasars. The baryon acoustic oscillation measurements improved in precision by a factor of roughly 2, with statistical uncertainties reaching approximately 0.24%. And the hint grew stronger. DESI combined with CMB data alone now showed a 3.1 sigma preference for evolving dark energy over the cosmological constant in a frequentist analysis. Combined with the DES 5-year supernovae, it reached 4.2 sigma. That is still below the 5 sigma threshold that physicists conventionally require to claim a discovery. But 4.2 sigma means there is roughly a 1 in 40,000 chance that the result is a statistical fluctuation. Mustafa Ishak Bushaki, a physicist at the University of Texas at Dallas and co-chair of DESI's Cosmological Interpretation Group, said it plainly. With a 4.2 sigma significance, I think we are getting to the point of no return. Will Percival of the University of Waterloo, co-spokesperson for the collaboration, was equally direct. It is looking more and more like we may need to modify our standard model of cosmology. The DESI paper itself contained a sentence that, for an academic publication, is remarkably blunt. Unless there is an unknown systematic error associated with one or more datasets, it is clear that LCDM is being challenged. Let me explain what it means if dark energy is truly evolving, because the implications are severe. In the standard picture, dark energy is constant. It never changes. It has been the same since the beginning of the universe and will be the same forever. The long-term fate of the cosmos under a constant cosmological constant is well understood and well documented. The universe expands forever. Galaxies beyond our local group eventually recede faster than light. The cosmic horizon shrinks. Stars burn out. Matter decays. The universe dies of thermal exhaustion in a cold, dark emptiness. This is bleak, but it is stable. The rules do not change. If dark energy is evolving, the rules are changing. The DESI best fit model suggests dark energy's equation of state crossed what physicists call the phantom divide, the boundary at W equals -1, roughly 5 billion years ago. Before that crossing, dark energy was in the phantom regime, with W less than -1. This is deeply strange. Phantom energy violates the null energy condition, one of the foundational assumptions of general relativity that guarantees energy density cannot be negative for any observer. Simple quintessence models, the most studied alternatives to a cosmological constant, cannot produce phantom crossing. The data are favoring something theoretically exotic, and the trend suggests dark energy is weakening. If it continues to weaken, the accelerating expansion could eventually slow, stop, and potentially reverse. The universe might recollapse, or dark energy might stabilize at a new value, or it might do something no current model predicts. The point is that the fate of the universe, which physicists have confidently described for 2 decades as eternal expansion into cold emptiness, is suddenly uncertain again. The future of the cosmos is no longer a settled question. DESI unsettled it in March of 2025, and almost nobody noticed. Now, there are legitimate reasons for caution. George Efstathiou at Cambridge has pointed out that the DES 5-year supernova dataset, which produces the highest significance, may contain systematic errors in its photometric calibration. A Bayesian reanalysis from 2025 found that when you apply the statistical penalty for introducing 2 additional parameters, the preference for dynamical dark energy over LCDM largely disappears for DESI plus CMB alone. The statistical method you use matters, but there is something else in the DESI data that is harder to dismiss. When you fit the standard LCDM model to DESI plus CMB data, the model returns an upper limit on the total mass of neutrinos that is less than 0.064 electron volts. Neutrino oscillation experiments have established that the sum of neutrino masses must be at least 0.059 electron volts. The LCDM fit is pushing below the physical floor. The math is producing a neutrino mass that is statistically consistent with being negative. Negative mass is not a thing. This is the model screaming at you that something is wrong. When you allow the dark energy equation of state to vary, this tension disappears. The neutrino mass limit relaxes to 0.63 electron volts, comfortably above the oscillation floor. Evolving dark energy fixes the neutrino mass problem. Whether this is a genuine signal or a coincidence of parameter degeneracies is an open question, but it suggests that the anomalies are not independent. They are connected, and DESI is not the only thing cracking. The Hubble tension is now, as of late 2205, at a significance exceeding 6 sigma. 6 sigma. In particle physics, 5 sigma is the discovery threshold. When CERN announced the Higgs boson in 2012, it was at 5 sigma. The discrepancy between how fast the universe appears to be expanding when you measure it locally using nearby supernovae and Cepheid variable stars, and how fast it should be expanding according to the cosmic microwave background and the standard model has passed a level at which, in any other context, you would declare that the model is wrong. The CMB, measured by the Planck satellite, gives a Hubble constant of 67.4 kilometers per second per megaparsec. The local measurement, led by Adam Rees and the SH0ES team, using over 1,000 orbits of the Hubble Space Telescope to observe Cepheid variables in the host galaxies of 42 Type 1a supernova, gives 73.04. The difference is about 8%. That does not sound like a lot, but the error bars on both measurements have been beaten down to the point where the gap is now yawning. The James Webb Space Telescope was supposed to help. It made things worse. In February of 2024, Rees and his team used JWST to observe over 1,000 Cepheid variables in distant galaxies. The result was essentially unchanged from the Hubble measurement. They rejected crowding, the idea that nearby stars blurring together were biasing the Hubble data at 8.2 sigma confidence. Rees wrote that with measurement errors negated, what remains is the real and exciting possibility that we have misunderstood the universe. Then, in August of 2024, Wendy Friedman and her Chicago Carnegie Hubble program team used the same telescope, JWST, to make an independent measurement using 3 different methods: Cepheids, the tip of the red giant branch, and carbon-rich asymptotic giant branch stars. Her combined result was about 70, right between Planck and SH0ES, with error bars that overlapped with both. Friedman declared that the standard model was holding up. Rees's group formally rebutted her analysis. 2 groups, the same telescope, fundamentally different conclusions. That is the state of precision cosmology in 2026. Dan Skolnick at Duke University, who measured a Hubble constant of 76.5 using the Coma cluster in early 2205, described the situation at the American Astronomical Society meeting with a single word: crisis. Niels Schoenberg at the Institute of Cosmic Sciences in Barcelona stated that the Hubble tension has reached the 5 sigma confidence threshold. and is currently considered the biggest crisis for the LCDM standard model. And it is not just the Hubble constant. There is the S8 tension, a disagreement between how clumpy the universe appears in weak gravitational lensing surveys versus how clumpy the CMB says it should be. The Planck prediction is that S8, a parameter measuring the clustering amplitude of matter, should be 0.832. Weak lensing surveys repeatedly found lower values, around 0.76 to 0.78. A 2 to 3 sigma discrepancy suggesting that matter in the universe is less clumped than the standard model predicts. The final KDS legacy results from March 2025 measured 0.815, which is much closer to Planck, potentially dissolving this tension. But other surveys at small scales still find low values, and the community has not reached consensus. What is happening here is not a single crack. It is a pattern of cracks. DESI says dark energy may be evolving. The Hubble tension says the expansion rate cannot be reconciled. Multiple independent measurements disagree with LCDM at the multi-sigma level simultaneously. No proposed fix resolves all the tensions at once. Early dark energy models that ease the Hubble tension worsen the S8 tension. Interacting dark sector models that fix one problem create another. A comprehensive analysis by Miller and collaborators in 2005 concluded that no combination of proposed modifications can successfully solve the Hubble tension within the current framework. You may have been told that Einstein's cosmological constant was his greatest blunder, and that he was wrong to include it. That framing obscures the actual problem. The real issue is not whether a cosmological constant should exist. Quantum field theory predicts that empty space should have energy and that energy should gravitate. The problem is the magnitude. The value of vacuum energy that quantum field theory predicts is roughly 10 to the 120 times larger than the value we observe. That is not a small discrepancy. That is one followed by 120 zeros. It has been called the worst prediction in the history of physics. The cosmological constant we observe is not just small, it is absurdly, inexplicably, pathologically small. And now DESI is telling us that even that inexplicably small number might not be constant. If the cosmological constant is not constant, it is not a constant. It is a field. It has dynamics. It evolves. It interacts with the expansion of the universe in ways that change over time. And that means the dark sector, which encompasses both dark matter and dark energy, is not a pair of separate mysteries. It is a single connected phenomenon that we have been artificially separating because our model told us to. And this brings us to the most uncomfortable convergence in modern physics. MOND says the dynamics of galaxies are governed by an acceleration scale connected to the Hubble constant. DESI says the Hubble constant itself may not be constant, that dark energy is evolving, that the expansion history of the universe is not what LCDM predicts. The Hubble tension says two different methods of measuring that constant give irreconcilable results. Verlinde says the connection between the acceleration scale and the Hubble constant is not a coincidence, but a prediction of emergent gravity. If all of these are pointing in the same direction, and they are, then the standard model of cosmology is not just cracking. It is cracking in a way that is consistent with a specific alternative, not a tweak, not a patch, a complete reconceptualization of what dark matter and dark energy are, and what space-time is. And the theoretical frameworks that might explain all of this say something about the nature of reality that is genuinely difficult to hear. Everything we have talked about so far has been about what we observe. Detection experiments that find nothing. An acceleration constant that connects galaxies to the cosmos. A standard model cracking at multiple seams simultaneously. These are all symptoms. What happens when you look at what the mathematics underlying those observations actually requires is something else entirely. We need to go back to Jacobson's 1995 paper. I mentioned it earlier, the paper that derived Einstein's field equations from thermodynamics. Now I need to explain what that derivation actually means, because its implications are the foundation of everything that follows. Jacobson started from the Bekenstein-Hawking formula, which says the entropy of a black hole is proportional to the area of its event horizon, not its volume. This is already strange. Normally, if you have a box of gas and you double the volume of the box, you roughly double the entropy, the number of possible microscopic arrangements of the gas molecules. Entropy scales with volume. That is how statistical mechanics works for every system we know about. Black holes are different. Their entropy scales with surface area. A black hole with twice the horizon area has twice the entropy, regardless of what is happening in the interior. This is called the area law. And when Bekenstein first proposed it in 1973, it seemed like a mathematical curiosity. Hawking confirmed it in 1974 by showing that black holes radiate with a temperature inversely proportional to their mass, which made the entropy formula exact rather than analogical. But neither of them fully reckoned with what the area law implies about the structure of space itself. Jacobson did. He combined the area-entropy relationship with the Clausius relation, a basic equation from thermodynamics that says the heat flowing through a system equals the temperature multiplied by the change in entropy. He applied this to a local patch of space-time, treating the causal horizon of an accelerating observer as a thermodynamic surface. He identified the heat flow with the energy flux through the horizon, and the temperature with the Unruh temperature, the temperature measured by an accelerating observer due to quantum vacuum fluctuations. From these ingredients, he derived the Einstein equation, the full tensorial Einstein equation, relating the curvature of space-time to the stress-energy tensor of matter, not an approximation, not a special case, the exact equation that general relativity uses to describe how mass and energy warp the geometry of the universe. His conclusion was devastating in its implications and modest in its prose. The Einstein equation is an equation of state, like the ideal gas law, like the equation relating pressure, volume, and temperature in a room full of air. The ideal gas law is true, it works, you can build engines and air conditioners and rockets with it, but nobody believes it is fundamental. It is an average description of what trillions of molecules are doing. Jacobson is saying that Einstein's equation, the equation that describes gravity, that describes the shape of the cosmos, is in the same category, true and useful and built on the same epistemic sand as any other emergent description. If gravity is not fundamental, then space-time is not fundamental either, because in general relativity, gravity is space-time. The curvature of space-time is the gravitational field. They are the same thing. If gravity is thermodynamics, then space-time is the thermodynamic medium. It is what you get when you average over the actual microscopic constituents of reality, and we do not know what those constituents are. This is not a fringe position. Jacobson's paper has over 1,200 citations. It has been discussed in textbooks. It influenced a generation of theoretical physicists, Thanu Padmanabhan, who held the distinguished professorship at the Inter-University Centre for Astronomy and Astrophysics in Pune, India, and who died in 2021, extended Jacobson's result to broad classes of gravity theories beyond general relativity. He showed that gravitational field equations quite generally reduce to thermodynamic identities on horizons. He described gravity as the thermodynamic limit of the kinetic theory of atoms of space. He proposed that the accelerating expansion of the universe is itself the emergence of new spatial degrees of freedom. Space is being created, not just stretched. When Padmanabhan died in September of 2021, at the age of 64, he left behind a body of work that had won prizes 8 times and a conviction that the deepest question in physics was not what dark matter is made of, but what space is made of. His death was a significant loss to the field at a moment when the ideas he spent his career developing are more relevant than they have ever been. The implications of the area law deserve more attention because they are genuinely strange and they connect directly to the dark matter problem. If the information content of a region of space is proportional to its surface area rather than its volume, then there are far fewer fundamental degrees of freedom in the universe than you would naively expect. A volume of space that appears to contain vast numbers of independently varying quantities, particles, fields, radiation is actually described by information on a 2-dimensional surface. The interior is in some deep sense redundant. It is a projection. This is the holographic principle, first proposed by Gerard 't Hooft in 1993. And given a string theoretic formulation by Leonard Susskind in 1994. Susskind later wrote that the 3-dimensional world of ordinary experience, the universe filled with galaxies, stars, planets, houses, boulders, and people, is a hologram, an image of reality coded on a distant 2-dimensional surface. That sounds like philosophy. It is not. It is a mathematical result derived from the properties of black hole horizons and supported by the most rigorously tested correspondence in string theory, Maldaceno's ADS/CFT. And then Mark van Ramsdonk took it one step further. Van Ramsdonk is a theoretical physicist at the University of British Columbia. In 2010, he submitted an essay to the Gravity Research Foundation competition titled Building Up Spacetime with Quantum Entanglement. It won first prize. And the argument it makes is, if you follow it carefully, one of the most disturbing ideas in modern physics. Van Ramsdonk worked within the framework of the ADS/CFT correspondence, a mathematical duality discovered by Juan Maldacena in 1997. ADS/CFT says that a theory of quantum gravity in a certain kind of spacetime, called anti-de Sitter space, is mathematically equivalent to a quantum field theory without gravity living on the boundary of that spacetime. This is sometimes called the holographic principle in action, because the lower dimensional boundary theory contains all the information about the higher dimensional bulk, the way a hologram encodes a 3-dimensional image on a 2-dimensional surface. What Van Ramsdonk showed is that in ADS/CFT, the spatial connectivity of the bulk spacetime, the fact that different regions of space are connected to each other and that you can travel smoothly from one region to another, corresponds to quantum entanglement between the degrees of freedom in the boundary theory. Entangled regions on the boundary give rise to connected regions of space in the bulk. Unentangled regions correspond to disconnected space. He then asked, what happens if you systematically reduce the entanglement? The answer is that the space-time begins to tear apart. Regions that were smoothly connected develop a constriction, a throat that grows narrower as entanglement decreases. In the limit of zero entanglement, the space-time pinches off completely. The two regions are no longer part of the same space. Let that sit for a moment. Quantum entanglement, the correlation between distant quantum systems that Einstein called spooky action at a distance, is not just a feature of matter living in space-time. It is the mechanism by which space-time itself exists. Entanglement is the glue. Remove it, and space falls apart. In 2013, Juan Maldacena and Leonard Susskind proposed the ER equals EPR conjecture, building on Van Ramsdonk's insight. ER refers to Einstein-Rosen bridges, commonly known as wormholes, hypothetical tunnels connecting distant regions of space-time. EPR refers to Einstein-Podolsky-Rosen entanglement, the quantum correlation between distant particles. Maldacena and Susskind proposed that these are the same phenomenon. Every pair of entangled particles is connected by a microscopic wormhole. Every wormhole corresponds to entanglement between the regions it connects. Susskind later wrote that quantum entanglement creates the spatial connectivity that sews space together. Without it, all of space would atomize. He was not speaking metaphorically in the mathematical framework of ADS/CFT. This is what the equations say. Space is not a container that exists independently and then has matter placed in it. Space is a network of quantum correlations. The distance between 2 points is a measure of how entangled the underlying quantum degrees of freedom are. Highly entangled regions are close together. Weakly entangled regions are far apart. Space is entanglement, measured in a particular way. If you find this difficult to accept, you are in good company. Einstein found quantum entanglement itself difficult to accept, calling it spooky action at a distance, and insisting that it revealed an incompleteness in quantum mechanics rather than a genuine feature of nature. He was wrong. Bell's theorem and subsequent experiments proved that entanglement is real and that the universe is fundamentally non-local. Now the suggestion is that this non-locality is not just a property of particles scattered through space. It is the reason space exists. Now think about what all of this means for dark matter. If space-time is emergent from quantum entanglement and gravity is its thermodynamic description, then the gravitational effects we attribute to dark matter might not be caused by a substance at all. They might be caused by the entanglement structure of the underlying quantum theory. The extra gravity in galaxies might be a consequence of how the microscopic information structure of reality organizes itself at low accelerations. The dark matter problem stops being about missing particles and becomes a question about the structure of space-time itself. Verlinde's 2016 paper makes exactly this argument. In a universe with a cosmological constant, the horizon carries entropy. Matter displaces some of that entropy. Space-time responds with additional gravitational force. That force looks like dark matter. But what you are seeing is a property of the emergence, a consequence of how space-time organizes itself, not a separate substance drifting through it. And there is another framework that bridges these ideas in a way that might be the most elegant proposal yet. In 2015, Lasha Beraziani and Justin Corey at the University of Pennsylvania published a paper titled Theory of Dark Matter Superfluidity. Their proposal is striking in its ingenuity. Dark matter, they suggest, does exist as a particle, a very light particle with a mass on the order of an electron volt. But in galaxies, where the velocity dispersion is low, these particles, Bose-Einstein, condense into a superfluid. Inside the superfluid core, excitations called phonons, which are collective oscillations of the condensate, mediate an additional long-range force between baryonic matter. This phonon-mediated force reproduces MOND phenomenology. The acceleration scale, A0, emerges from the properties of the condensate. In galaxy clusters, where the velocity dispersion is much higher, the dark matter temperature exceeds the critical temperature for condensation. The dark matter is in its normal phase, not the superfluid phase. In this regime, it behaves like standard cold, dark matter. No MOND, no extra force. Just gravity from invisible particles. This is extraordinarily clever. It means MOND and cold dark matter are not competing explanations. They are different phases of the same substance, like ice and water. In galaxies, the dark matter is ice, a coherent quantum state with collective behavior that modifies gravity. In clusters, it melts and you get ordinary particle dark matter. The theory naturally explains why MOND works so well for galaxies and fails for clusters. The debate between MOND and dark matter dissolves. You are looking at the same thing in two different thermodynamic states. Bereziani and Khoury received the 2017 Buchalter Cosmology Prize for this work. There is also an active experimental battleground that has the potential to resolve some of these questions, and it involves the simplest possible gravitational system. Two stars orbiting each other, wide binary stars, pairs of stars separated by distances large enough that their mutual gravitational acceleration falls below Milgrom's threshold, should behave differently in MOND than in Newtonian gravity. In 2023 and 2024, Kyu-Hyun Choi at Sejong University used data from the European Space Agency's Gaia satellite on roughly 26,500 wide binaries and found deviations from Newtonian dynamics consistent with MOND at approximately 5 sigma significance. If confirmed, this would be a direct detection of modified gravity in the solar neighborhood. No dark matter required. But Indranil Banik and collaborators, using different statistical methods on overlapping data, found a 19 sigma preference for Newtonian gravity. Same stars, same satellite. Opposite conclusions. The disagreement is unresolved as of early 2026 and comes down to differences in sample selection, contamination treatment, and statistical methodology. It is perhaps the single most important ongoing test in gravitational physics, and it is being conducted not with a billion-dollar underground detector, but with a catalogue of nearby stars that anyone with access to the Gaia database can examine. But notice what all of these theories share. Whether you follow Verlinde's emergent gravity, Jacobson's thermodynamic derivation, Van Ramstonck's entanglement-based spacetime, or Bereziani and Khoury's superfluid dark matter, you end up in the same place. Dark matter is not what we thought. Spacetime is not what we thought. Gravity is not what we thought. The universe has a structure beneath the structure we perceive, and what we have been calling dark matter is either a consequence of that hidden structure or a substance whose behavior is governed by that structure in ways the standard model cannot capture. The detection experiments are not failing because of inadequate technology. They may be failing because the question they were designed to answer is the wrong question. You do not find the answer to a thermodynamic question by looking for a thermodynamic molecule. There is no such thing. Temperature is real. You can measure it. It has physical effects. But there is no temperature particle. If dark matter is the gravitational equivalent of temperature, an emergent macroscopic effect of underlying microscopic structure, then building a bigger xenon tank will never detect it. You cannot catch emergence in a bottle. This is not the same as saying dark matter is imaginary. It is real. Its gravitational effects are measured to extraordinary precision. But the thing that is real might not be a thing. It might be a property of spacetime, a consequence of entanglement, an elastic response of the vacuum, a signature of information. The cosmic web, the vast network of dark matter filaments that connects galaxies across the observable universe, was detected directly for the first time in January of 2025 using the Subaru telescope's Hyper Suprime Cam. These filaments contain 35% of all cosmic mass within less than 1% of cosmic volume, with average densities 60 times the cosmic mean. They are real. They are measurable. They form the scaffold on which every galaxy, every star, and every planet in the universe is built. But what if the scaffold is not made of particles? What if it is made of space-time itself, organizing under its own hidden rules, forming structures that we can detect gravitationally but can never catch in a detector? Because catching them would require you to bottle up a piece of geometry. There is a dark matter stream passing through our solar system right now. It was identified using data from the European Space Agency's Gaia satellite in 2017 and 2018 by Ciaran O'Hare and colleagues. They called it the S1 stream. It is the remnant of a dwarf galaxy that the Milky Way consumed billions of years ago, comprising roughly 30,000 identified stars moving on a counter-rotating orbit. O'Hare published a paper titled "A Dark Matter Hurricane," showing that the dark matter in this stream is washing through the Earth at roughly 500 kilometers per second. You are inside it right now. Something is passing through your body at 500 kilometers per second, exerting gravitational force, shaping the orbits of stars around you, and the most sensitive instruments ever built cannot detect it directly. Either it is made of particles so exotic that they interact with nothing we can build a detector from, or it is not made of particles at all. The 40-year assumption has been that the first option is correct. The accumulating evidence increasingly suggests we should be seriously considering the second. And that brings us to the part of this that I have been building toward. The part that takes everything we have discussed and follows it to its logical conclusion. A conclusion that is supported by published, peer-reviewed physics. A conclusion that the people who understand it best would rather not state plainly. Here is what the evidence says, stated without hedging, without diplomatic qualification, without the careful language that academic papers use to avoid saying what they mean. The universe is made of something we cannot see, cannot touch, cannot detect directly, and cannot identify. This something constitutes 85% of all matter and 27% of the total mass energy content of the cosmos. We have known it exists for 90 years. We have spent 40 years and billions of dollars trying to catch a piece of it. We have improved our detection sensitivity by a factor of 100 million. We have found nothing. And the experiments are now approaching a physical limit beyond which detection becomes impossible, regardless of how much money you spend. Meanwhile, an Israeli physicist wrote down a formula in 1983 with a single adjustable parameter that predicts the gravitational behavior of galaxies better than dark matter models with multiple parameters. His formula was rejected by the leading journals and ignored by the mainstream for 4 decades. An American astronomer tested the formula against his own data, found it worked, and described the experience as the most difficult struggle of his career. A tight universal correlation between baryonic matter and total gravitational acceleration was confirmed across thousands of independent measurements in 2016. The physics community's response was to continue building xenon detectors. A Dutch string theorist proposed in 2010 and 2016 that gravity is not a fundamental force, but an emergent consequence of information and entropy, and that dark matter effects arise naturally from the thermodynamic behavior of space-time in a universe with dark energy. His zero-parameter prediction matched weak lensing data from 33,000 galaxies. The physics community's response was mixed interest and continued investment in particle detection. A Czech-British team showed in 2021 that a relativistic version of MOND can reproduce the cosmic microwave background, eliminating the last theoretical objection that had been used to dismiss modified gravity for 30 years. The physics community's response was to call the theory Baroque. The largest three-dimensional map of the universe, released in 2005, shows evidence at up to 4.2 sigma that dark energy is evolving rather than constant. The Hubble tension has exceeded 6 sigma. The standard model of cosmology is under more simultaneous pressure than at any point in its history, and the theoretical framework that best explains why all of these anomalies are appearing at once. The framework where gravity is emergent, space-time is woven from entanglement, and dark matter is a consequence of the underlying information structure of reality, is the framework that the fewest resources have been dedicated to testing. I want to be clear about what I am not saying. I am not saying that MOND is definitely correct. I am not saying that dark matter particles definitely do not exist. I am not saying that LCDM is definitely wrong. The data are not yet decisive on any of these questions. What I am saying is that the data are pointing with increasing insistence in a direction that the physics community has been reluctant to look. And the direction they are pointing is this: space-time may not be what you think it is. You experience space-time as the stage on which physics occurs. Things happen in space and over time. Matter moves through space. Light travels through space. You sit in a chair in space and time passes. This seems so obvious that it barely requires stating. But what Jacobson showed in 1995, what Verlinde showed in 2010, what Van Ramsdonk showed in 2010, what Maldacena and Susskind showed in 2013, is that space-time is not the stage. Space-time is a description, an emergent, approximate, macroscopic description of an underlying quantum reality that we do not yet have a complete theory for. The analogy that physicists use most often is the one Jacobson used: sound waves in air. The equations that describe sound waves are perfectly valid. You can use them to design concert halls and jet engines and hearing aids. But sound is not fundamental. Sound is what you get when trillions of air molecules move collectively. The equations that describe sound are an emergent, macroscopic description. If you tried to understand air by quantizing the sound wave equation, you would get nonsense. Air is not made of sound. Sound is made of air. Jacobson is saying that gravity might be in the same category. The equations of general relativity are the wave equations. They work. They let you predict the orbits of planets and the bending of light and the expansion of the universe. But they may not be describing anything fundamental. They may be an emergent description of something deeper, something made of quantum information, an entanglement and degrees of freedom we have not identified. If this is true, it changes the dark matter problem completely. If space-time is emergent, then the gravitational field is emergent. If the gravitational field is emergent, then deviations from the expected gravitational field at low accelerations, which is what we call dark matter, might not be caused by extra stuff. They might be caused by the emergence breaking down. The way that the equations governing sound in air break down at very high frequencies, where the wavelength approaches the spacing between individual molecules and the continuum description fails. The equations do not fail because there is extra sound you cannot hear. They fail because you have reached the resolution limit of the description, the radial acceleration relation, the tight correlation between baryonic matter and total gravitational acceleration that McGaw and colleagues documented across 153 galaxies, is exactly what you would expect if dark matter were an artifact of emergent gravity breaking down at a specific scale. Below Milgrom's acceleration threshold, the emergent description loses its accuracy. Additional gravitational effects appear, not because there is extra mass, but because the approximation is no longer valid. The reason the effects correlate so tightly with baryonic matter is that the baryonic matter distribution is what determines the gravitational field in the first place. There is no mystery about why dark matter knows where the baryons are. It is not a separate substance that somehow communicates with ordinary matter. It is a feature of how the baryonic gravitational field degrades when the emergent description reaches its limits. This is why the detection experiments find nothing. You cannot detect an artifact of emergence. You cannot put the breakdown of an approximation in a bottle. The particle they have been looking for does not exist as a particle. It exists as a property of space-time itself, and the DESI results, the Hubble tension, the evolving dark energy, all of it starts making sense under this framework. If space-time is emergent, the cosmological constant is not a fixed number. It is a thermodynamic property of the underlying system, and thermodynamic properties can change as the system evolves. Dark energy evolving is not a crisis. It is expected. The Hubble tension, two different ways of measuring the expansion rate, giving two different answers, might not be a measurement error. It might be telling you that the emergent description of space-time gives different results depending on where and how you probe it, because it is an approximation, and approximations can be self-consistent within their domain of validity while disagreeing at the boundaries. Let me return to the people. Fritz Zwicky saw the scaffolding in 1933. He measured the mass of the coma cluster and found 400 times more than the visible stars could account for. He was ridiculed for his personality and ignored for his physics. He died in 1974, 5 years before the gravitational lensing he predicted in 1937 was confirmed. Vera Rubin measured the scaffolding in the 1970s. She documented flat rotation curves across more than 60 galaxies and proved that the invisible mass was real and pervasive. She was denied the Nobel Prize, in part because the Nobel Committee at the time did not award prizes for observational discoveries, in part because she was a woman in a field that told women they could not apply. She died on Christmas night in 2016, and the universe does not care about the Nobel. Mordechai Milgram wrote down the equation of the scaffolding in 1983. A single number, a single acceleration threshold, rejected by nature, rejected by the leading journals, ignored by the community for 40 years while his predictions quietly came true, one after another. Stacy McGaw tested the equation against his own data and found that it worked. He described the realization as the most difficult struggle of his career. His grant proposals were harshly rejected. He is still fighting the same fight, still publishing the same inconvenient results, still being treated as a heretic by a community that has not offered a better explanation. Erik Verlinde proposed that the scaffolding is space-time itself, responding to the presence of matter in ways that general relativity, as an emergent approximation, cannot fully capture. He was told his ideas were not even wrong. He continues to work on them. The pattern is consistent. Every time someone gets close to the architecture beneath reality, the institutions designed to understand reality resist. This is not a conspiracy. It is something more human. It is the collective inability of a scientific community to admit that a question it has been working on for 40 years might have been the wrong question all along. It is the sunk cost fallacy operating at the scale of an entire discipline. Billions of dollars of infrastructure, thousands of careers, decades of institutional momentum, all invested in the assumption that dark matter is a particle. Admitting that it might not be requires more than updating a model. It requires acknowledging that the model, the framework, the very conceptualization of the problem was wrong from the start. Consider the numbers. 5% of the universe is ordinary matter, the atoms that make up stars, planets, your body, everything you have ever touched or seen or measured directly. 27% is dark matter. 68% is dark energy. 95% of the mass energy content of the universe is dark. We do not understand it. We have never directly detected it. We have no confirmed theory for what it is, and the model we have been using to describe it, LCDM, is now cracking at multiple seams simultaneously. This means that the most successful civilization in the history of Earth, one that has split the atom, sequenced the genome, landed on the moon, and photographed black holes, does not understand 95% of the universe it lives in. We are not close to understanding it. We may be asking the wrong questions about it, and the people whose job it is to figure it out have spent 4 decades digging increasingly sophisticated holes in the ground and listening for a particle that may not exist. There is a paper from 2025 on the ArcSieve that proposes holographic dark matter, a framework where dark matter does not arise from particle physics at all, but is derived from the infrared cutoff set by the cosmic horizon scale. Dark matter as a property of the boundary of the observable universe. Dark matter as information encoded on the surface of all that you can ever see. The Royal Society Interface Focus published a paper the same year, stating that if quantum entanglement turns out to be fundamental, as holography maintains, then the properties we had previously taken to be fundamental, including space-time, gravitation, and the particles and forces in the standard model, turn out to be features of an emergent description. Features of an emergent description. That is what they are calling reality. The chair you are sitting in, the body you inhabit, the light entering your eyes as you watch this. Emergent features, not fundamental, not bedrock. Descriptions and dark matter is the first place where the description visibly fails. We noticed it 90 years ago. We spent 40 years trying to patch the failure by inventing a particle. The particle was never found, and the reason it was never found may be the reason that changes everything we think we know about the nature of existence. Dark matter is not a gap in our model. It is a crack in the description itself, a place where the emergent approximation of spacetime lets the underlying structure show through. The scaffolding behind the stage, the stitching in the hologram, the resolution limit of reality. You were never supposed to see it. Emergent descriptions are, by their nature, self-concealing. You do not notice that air is made of molecules when you are listening to music. You do not notice that temperature is made of kinetic energy when you are feeling warmth on your skin. The emergence works so well over such a vast range of conditions that the underlying structure becomes invisible. But at the edges, at very low accelerations, at the farthest reaches of galaxies, in the spaces between galaxy clusters, in the expansion rate of the cosmos itself, the emergence phrase, the stitching shows, something underneath becomes visible. That something is not a particle drifting through a tank of liquid xenon underground. It is the structure of reality itself, the quantum information that space-time is made of, the entanglement that holds space together, the thermodynamic architecture from which gravity emerges. Zwicky saw it. Rubin saw it. Milgram wrote its equation. Verlinde proposed its origin. Van Ramsdonk described its mechanism. And every year, more data arrive that make it harder to look away. 5% of the universe is the matter you can see. The other 95% is not missing. It is the architecture, the medium, the fabric that the 5% is woven into. And we called it dark because we could not see it. The way a fish calls water invisible because it has never experienced anything else. The water is not invisible. The fish just does not have the instruments to see it. And for 90 years, neither did we. But the cracks are widening. The detectors are finding the wrong particles. The equations are disagreeing with each other. The expansion rate cannot be reconciled. The cosmological constant is not constant. The scaffolding is showing. And the most unsettling part is not what the scaffolding is made of. The most unsettling part is what the scaffolding implies. If space-time is emergent from entanglement, then the universe is not a place. It is a process, a computation, a structure that generates the appearance of space and time from something that is neither spatial nor temporal, something that does not exist anywhere, because where is part of the description it generates. Dark matter was our first clue that the description has edges, that reality as we experience it is a projection, and the data that have accumulated over the past 90 years, from Zwicky's coma cluster to LZ's subterranean silence, to DESI's cracking map, to Verlinde's entropic equations, all point in the same direction. The projection is not the whole story, and we are only beginning to see the shape of what lies beneath it.